So welcome, we'll proceed with the next problem on the permeability of soil chapter. In this problem, the statement is as follows. The figure below shows the setup of the water filter. So this is a water filter, and we have been asked to find it out the quantity of the water which is filtered in a clay for a day. So for one day, how much quantity of water that can be filtered through this setup, and they have again asked us to draw about the total, neutral and effective stress diagram. So as you see here, the total head at this particular face is higher. This is the total head at this particular level A, and at this face the total head is this one. So since the level at this particular point A, there is high head as compared to this face, so therefore the flow will be occurring in downward direction. So remember, the demarcation or the investigation of this particular direction of the flow is very important in order to deal with such kinds of problem. But we have asked to again to evaluate the amount of water which can be filtered through a clay, which is again a very simple problem, and for that we have been given the data of the coefficient of permeability. So from the concept, Q becomes equal to area into velocity. The area of flow is given it as 3.14 meter square. This is the area of flow, or the plan area of flow, which is 3.14 meter square. From the Darcy's equation, V becomes equal to K into I, and again over here K is also given it as 6 into 10 raised to minus 3 centimeter per second, and also you need to evaluate the I. Obviously the length of the travel or the length of the flow is 2.5 plus 1. So L will be, or length of the soil specimen throughout which the flow will be occurring, is 3.5 meter, and the head loss, which is very important to determine. So over here the head loss will be at level 1 and at this particular level 1. So if you insert a piezometer at the bottom of the soil, you will observe the water to be rise up to this particular level. So that's how the question is smartly given in terms of the setup values. So since the water will be rising up to this level, you will have this particular level. I consider again this as a diagram in order to calculate the head loss. Total head loss will be difference between this and this particular level. This is the total head loss H, which is responsible for a flow to occur, which is nothing but 4 plus again 2.5. So hence it will become 6.5. H will become 6.5 meter. So therefore I becomes equal to H by L, 6.5 by 3.5. So we'll get I value equals to 6.5 by 3.5, 1.857. So we'll get I value. So you need to place all these values I, K, A in this particular expression 1. So Q becomes K I A, which is equals to K is 6 into 10 raised to minus 3. Again I need to convert it in the meter, so it becomes 10 raised to minus 2 meter per second, and I is again unitless, 1.857 into area obviously is in meter square, so there is no need to change or convert the into unit. So Q will become equals to 6 into 1.857 into 3.14. You'll get Q equal to 34.99 meter cube per second, obviously into 10 raised to minus 5 into 10 raised to minus 5 meter cube per second. But in the question what is asked, amount of the water which can be filtered in a day. So for a day obviously there are 24 hours the water will be filtering. I am assuming 24 hours, so it became 24 into 3 3600 second. So again you need to multiply by the value equal to 24 into 3600, because I assume the plant to be working throughout a day. But if it has been given that the efficiency, working efficiency equal to 30%, 40%, then you need to multiply by that factor into 24 hours. So which indicates only that much of the time the filter is working. So therefore, if you solve this, if you evaluate this, you will get the quantity of water which is filtered, Q, equals to 30.22 meter, 30.22 m cube, 30.22 m cube. So this is the answer for the step 1 of the problem number 6. So what I did, I just used the simple formulation and just multiply by the time value throughout which the plant is working, and by that I have determined the amount of the water which is filtered in a clay. So the next problem is about the total, neutral and effective stress diagram. So first of all, it is very easy for me to draw a total stress diagram, and I will draw later on the neutral stress diagram or the pore water pressure diagram, and based on these two diagrams I can easily draw effective stress diagram, because just effective stress is the difference of total stress minus the neutral stress. Hence it is very important to initiate with the second part of this problem with the total stress diagram. So but in order to calculate a total stress, I again need the diagram and the gamma sat value of the particular soil. So for that the data is given in terms of specific gravity of the soil and the porosity of the soil. So from the data given, the gamma sat, remember the key is to mug up all the formulas. If you cannot mug up, remember the smart way to remember all of these. Gamma sat will be G plus E divided by 1 plus E into gamma W. Gamma W in the problem is not given, so you can take it as 9.81 kilonewton per m cube, and E is not given, but rather than E the porosity N is given. Porosity N is given. So therefore from that N equals to 0.4, 40% porosity. From that you can calculate E. What is the relationship? Again 1 plus E will be equal to 1 by 1 minus N. So it becomes 1 by 0.6. It becomes equal to 1.667. So therefore E becomes equal to 0.667. So you need to place this value of E in this equation. So we'll get the gamma sat equals to, G value is given it as 2.65 plus 0.67 divided by 1.67 into 9.81, and you will get the value in kilonewton per m cube, or value of gamma saturated. So uh, 2.65 plus okay, fine. We'll get gamma sat as 19.503 kilonewton per m cube. So you must calculate this particular value, because this is very important in order to draw a total stress diagram. So I'll redraw a figure again for you, and on this figure I am drawing the neutral and effective stress diagram. This is the soil. I think the soil length is 3.5 meter, and the water level is like this. and this particular level is 4 meter, and this is 2.5 meter, and this is 1 meter. So this is the water level at the exit face of the soil. This is the water level at the entry face of the soil, and I'll extend these particular levels in order to draw the total, neutral and effective stress diagram. So I'll draw over here total stress U, neutral stress neutral stress U, and total stress sigma, and effective stress we denote it by sigma dash. So sigma dash is just sigma minus U, total stress minus neutral stress diagram. So so over here the total stress acting at this particular point, it is exposed to atmosphere, and so gauge pressure will be 0. So 0 will be the pressure, effective stress, total stress is 0. But if I come to this particular level, so the stress will be equal to gamma W into 4. So therefore it becomes gamma W is 9.81 into 4, it becomes 39 point. So this value will be gamma W into 4, so which is 39.24 kPa or kilonewton per meter square, this particular value. Or I'll write over here as this particular value as 39.24. So I'll take all the units in kPa. This is the 39.4 value, and if I just go down and I reach to up to let's suppose this particular level, how to find out this particular value? Just you need to add it 39.24 plus gamma sat into 2.5. So at this particular level, let's suppose AA, at level AA, total stress will be equal to gamma W into 4 plus gamma saturated, because total that means gamma sat you need to take, into 2.5. So it becomes 9.81 into 4 plus gamma saturated we calculated 19.503 into 2.5, which becomes equals to 19.503 is the saturated unit weight of the soil. So the total stress acting at the level AA will be 87.99 kPa. So it will be like this, 87.99 kPa. Or I can take it as 88 kPa. This is that value, 88 kPa. And if I take this particular level, then hopefully at bottom of the soil, at bottom the sigma will be equals to 9.81 into 4 will remain as it is, plus gamma saturated, which is 19.503 into the length equal to 3. So this particular total stress will become equal to, or I can add just 19.503 to this particular value, you'll get 107.5. So, and the same slope will go on continue. This particular value is 107.5 kPa at the bottom of the soil. This particular value, total stress value, 107.5 is very easy to calculate. 107.5. Now the complicated thing will come, evaluation of pore water pressure, which is not easy to calculate. Remember, it is not easy to calculate. So in order to calculate, you need to place a piezometer inside the soil sample, and you need to measure the water level at which the water has been rise in this piezometer level. So the U for this particular case is, if you insert the piezometer over here, you will not get any rise in the water level except capillary. So you will get the same rise of the water level, but if you insert in between, suppose if I have inserted over here, you will get the rise of the water level equal to this particular height. You will again get this particular height. That means the point at which you have inserted, you will get that particular height or rise in particular water level at that particular height. So therefore the neutral stress will become same as that of the total stress. So the path will become same. So the value will also remain same, 39.24 kPa. But once the soil starts entering it into a soil, once the water starts entering into a soil, the scenario will change. And how it will change, I will tell it to you. If I just insert a piezometer at the end of the soil, because that's what we have did it in our previous session as well, then water will rise up to a particular this level, right? And also we have find out one factor which is nothing but I, which is equals to 1 point, hopefully we have calculated in our previous discussion, 1.857 here, I, which is nothing but the head lost divided by length of the flow or length of the soil. So so therefore if I just want to calculate the pore water pressure at this particular stage, it is 39.24, but if I insert the piezometer at this particular end, then pore water pressure will be equal to 9.81 into just the value equals to 1. Plus similarly we have got the different values of pore water pressure in between all these values. So I will proceed with it, but I'll again consider one more example. If I insert the piezometer at suppose level AA, then how much I will get the rise in the water level? How much I will get the rise in the water level if I insert the piezometer at AA? So at level AA, I'll again continue with the discussion of the pore water pressure U. See, the length of the travel up to level AA will be equal to 2.5 meter. So at AA length will be 2.5 meter. See, if you travel by 3.5 meter, the 6.5 meter will be the total head loss. So I'll write it like this on the next page, fresh page. If you travel, or if the water travels, by 3.5 meter, then head loss will be 6.5 meter. So if the water travels by 2.5 meter, then head loss will be how much? I consider it as x. So if it travels by 3.5 meter, head loss will be 6.5 meter. So hopefully you will got it. If you travel by 3.5 meter, head loss will be from this to this end, which is nothing but 6.5. But if the water travel from this to this, that is 2.5 meter, then what will be the head loss? Therefore 3.5 into x equals to 6.5 into 2.5. So therefore head loss you will get in terms of x, which is nothing but 6.5 by 2.5 divided by 3.5. So get x as 4.643 meter, which is nothing but the head loss. Remember, this is the x is nothing but head loss. So if I again go back to the discussion, head loss from this particular level to this level is this particular value is 4 point, so we have calculated 4.643 meter. 4.643 meter. This is the head loss from this is the 4 meter, right? And within the soil it has gone up to this particular level of the water, let's suppose with the scale, so it's 0.643 meter. So if this is 0.643 meter, then the balance will be 2.5 minus 0.643. So you will get 2.5 minus 0.643 as 1.857. So the level increase will be from this particular level is I think 1.857. So I hope you got by this particular value of 1.857 how we have arrived. We have calculated if you travel by 2.5 meter, what will be the head loss. So head loss will be from top level to this particular level. Total head loss we got it by 4.643. Since this is the 4 meter, I have deducted 4 meter from that. So therefore within the soil we have been entering up to value of 0.643, but this particular we know the value equals to 2.5. So again I have deducted 2.5 in order to calculate or evaluate the level of the water in the piezometer which is inserted at AA. So hence we got it by 2.5 minus 0.643, we get it as 1.857. So therefore you here will become 9.81 into 1.857, and if you do it, then you'll get the pore water pressure equals to 18.22 kPa at level AA. So this calculation is confirming to level AA, and this is at the bottom level calculation. So therefore at level AA you get the pore water pressure to be equal to so that means if this is a 39.24, it will get reduced up to 18.22 kPa, and this is the 18.22 kPa value, because graphically if I want to draw it will be like this, 18.22 kPa. And again if I just go to the bottom, it will be 9.81 into 1, so it will become only 9.81 pore water pressure at the bottom. I'll write it over here. At bottom you will be 9.81 into piezometer, the level of the water at which it is been risen in the piezometer is nothing but just the pore water pressure U. So it becomes 9.81 kPa. So this value is 9.81 kPa. The small value less than 18.22, this is 9.81 kPa. And if I just want to draw effective stress diagram, you need to deduct this particular small triangle into this particular big triangle. If you do it, it is very easy, just the arithmetic. Since this will get balanced, so effective stress over here become 0. Effective stress over here will be at suppose level 1. I need to calculate effective stress. Sigma dash will be 88 minus 18.22. You'll get it as 88 minus 18.22, you will get 69.78 kPa. So get this particular value as 69, hopefully 69.78 kPa. This is that particular value, 69.78 kPa, and at the bottom 107.5 minus 9.81. So sigma dash will be 107.5 minus 9.8. You'll get, I'll write direct value at the bottom. This particular value as 97.69 kPa. So even just by knowing this particular value of 97.69, you can calculate in between, because the triangle, the slope of line has to remain constant. So you can check it out just by multiplying by a factor of 2.5 by 3.5. So you'll get the same answer, 69.78. So I'll rewrite a check over here, because for effective stress I'll write check in this particular box, how to check whether your problem is correct or not. For the effective stress at this particular, this is the level AA, and this is the bottom level, this is the entry level, this is the triangle, and effective stress at bottom we have got it as 97.69, and this particular length is 2.5 meter, and this is 1 meter. So in order to check, sigma dash at level AA will be equal to sigma dash at bottom 97.69, and from property of similarity of triangle, this by this will be equal to this by this. So that's what we are interested in, sigma dash at AA. So from that, sigma dash at AA divided by 2.5 equals to 97.69 divided by 3.5. So you will get as 2.5 by 3.5, you will get sigma dash AA, the same value, equals to 69.778 you will get, which is nothing but the same value as that of you got it from your calculation of the pore water pressure at that particular level. So this completes your problem number 6 in the permeability of soil chapter. Thank you.